this question, we're supposed to find the parameterization of the osculating circle at t equals pi over 4 for r of t equals cosine t sine t. Okay, so the first thing to do is to check, well, just in general, for an osculating circle, what we'll need is the radius of curvature and the center. Okay, and then we can write our formula, construct the parameterization. So for the radius, though, we'll need curvature, right? Because radius is 1 over the curvature, 1 over the curvature at the certain point. Okay, and then the center just has a totally different formula, and we'll get to that as the problem goes along. Okay, so the first thing to check to find for curvature is to see if it's an arc length parameterization. So check for arc length parameterization. So let's check if the magnitude of r prime of t does this equal 1. So let's see. So r prime of t is going to be negative sine t and cosine t, a positive cosine t. So if we take the magnitude of that, if we're going to square both components, so we get sine squared t plus cosine squared t, all under the square root sign, then yes, this is going to be an arc length parameterization. So what that means is that we don't have to go through the whole entire process of like finding the arc length formula and then finding the inverse and then plugging it back in and all of that messy stuff. We don't have to do that, and we don't have to use the kind of disgusting formula that we just used on the previous problem. So what we're going to do is actually just rewrite this parameterization, and I'm just going to stick an S in there because we're good on the arc length parameterization side there. Okay, so this is going to be cosine S and sine S. Okay, so that just tells us we're working with an arc length parameterization, meaning that the magnitude of the derivative was equal to 1, is always going to be equal to 1. We're at constant speed here. Okay, so now what we're going to do is apply the easier formula for curvature. So k of s is equal to the magnitude of the derivative of the unit tangent vector with respect to s. So t of s, that's what we have to find first. So t of s, our unit tangent vector, so we have to find the unit tangent vector first before we even derive it, and then take the magnitude. So it's kind of like a building step-by-step process here. So we're going to find the unit tangent vector, and that's found by taking the derivative of our parameterization, of our arc length parameterization, and then dividing by that vector's magnitude. Okay, so this, let's see what we get here. So r prime of s is going to be negative sine s, comma cosine s, okay? And then on the bottom, we know that this is already an arc length parameterization, right? So this is automatically going to equal, no, it is not. Okay, it's not automatically going to. It just happens to be that the magnitude of our r prime of s is going to equal 1, okay? So that's just going to equal 1. So this is our unit tangent vector right here, okay? And then we'll continue from there. So we found that our unit tangent vector is equal to negative sine s and a cosine s. Okay, so now to find the curvature, so we have to take the derivative of this, okay? So t prime of s is equal to negative cosine s and then a negative sine s, okay? And for the curvature, now all we need is to take the magnitude of this, so dt ds, which is the same thing as saying magnitude of what we just found, so t prime of s. It's the same thing, different notation, okay? So we're going to square these, so that'll become cosine squared s plus sine squared s, all right? And this is actually going to be pretty simple. It's going to work out very nicely and be a 1. Okay, so the curvature is going to be 1. And that's k of s. And this is at any value of arc length. But no matter what the value of arc length, this is always going to be a constant 1. So we can assume that it's the same when t is equal to, so this is going to be the same when t is equal to pi over 4. It's not going to matter. Curvature is always going to be 1. For this problem anyways, okay? So that means that our radius of curvature is going to equal 1 over the curvature at our point. So that's going to be 1 over 1, which again is just going to be 1. So that's very convenient. All right, so we found our radius, and the next thing that we have to find is the center. Okay, so the center, OQ, is equal to r of t naught. Okay, so our original parameterization evaluated at the point that we're looking at, plus our radius of curvature times the unit normal vector evaluated at the point we're looking at. Okay, so the first thing is to find r of t naught, and t naught in this case is pi over 4. That's what we're given as our t value. So this is going to equal, let's see, cosine pi over 4, comma, sine pi over 4. Okay, and this is just going to be, both of them are going to be positive, radical 2 over 2 and a radical 2 over 2. Okay, perfect. So now that we found that, now we're going to find, we know that r is 1, our radius of curvature is 1 all the way around, and our unit normal vector is going to be the following. It's found by taking the derivative of the unit tangent vector, okay, and then dividing by the magnitude of that derivative of the unit tangent vector. Okay, so this is going to be, well, actually, let's aim for, okay, ignore that. Let's aim for n of the unit normal at pi over 4, so we can pin it down to a point, right? So this is going to be the derivative of the unit tangent vector at pi over 4 divided by the magnitude of that vector, okay? So we have something like that. Okay, so now let's solve for both of these. So the first one, the derivative of the tangent vector of the unit tangent at pi over 4 is going to equal, so we have that this was a negative cosine t negative sine t, so now we're going to have negative cosine pi over 4 and negative sine pi over 4. Okay, so that's going to be a negative radical 2 over 2 and another radical 2 over 2. Okay, so that's for t prime. And then if we take the magnitude of this, so let's see what we get there. T prime pi over 4 is going to equal each of these squared. So basically 2 over 2. And then, no, 2, I can't square things. 2 over 4 plus a 2 over 4, which is 1/2 plus 1/2. So that means that the magnitude is just going to be 1. Okay? So for our normal vector, for our unit normal, I'm going to plug them in here. So we found that this equals 1. Okay, so that's a 1 on the bottom. And our t prime at pi over 4 is equal to negative radical 2 over 2, comma, negative radical 2 over 2. Okay, so that's our unit normal vector. And we found our r of t naught, which was a positive version of that. And then we have 1 as our radius of curvature. So let's put it together for the center on the next slide. So our center, which is given by, noted by OQ, is equal to our r of pi over 4, which was radical 2 over 2, and another positive radical 2 over 2. And then this is plus our radius of curvature, which was a 1, and then our unit normal vector at t over 4, t equals pi over 4, was equal to negative 2 over 2 and a negative 2, radical 2 over 2, radical 2 over 2. Okay, so as you can see here, when we add these across, we're actually going to get that the center itself is going to be at 0, 0. Not too exciting, but it's demonstrative of what we need to do for an osculating circle. So anyway, so this is the center, all right, that it just happens to be at the origin, okay? So now that we found the center and the radius equals 1, remember? So now we're just going to plug that in. So our parameterization for the osculating circle is going to be the OQ, which is the center, plus our radius, whatever we found that to be, times cosine t, comma, sine t. Okay, so this is going to be, when we plug those in, we just get 0, 0 for that, plus 1 times cosine t, sine t. Okay, so now at this point, we just make the final leap here and kind of just get rid of that and get rid of that. So we're left with c of t is equal to cosine t, sine t, which you might recognize as the unit circle centered centered at the origin. So I must say that actually that problem actually turned out quite nicely. What with the pleasant numbers and all, like the ones and the zeros. But anyways, I think it was demonstrative of the process that you can go through to find that osculating circle. Finding the radius of curvature, and then the center of curvature via the unit normal vector, and then plugging them both into the final parameterization. So again, what I'm boxing now is our answer for the parameterization of the osculating circle at t equals pi over 4. Okay, so that's about it for the practice problems video. I hope that helped, and I'll talk to you in the next video if you watch.